Okay, so let me begin. So today I'm going to talk about, this is R means the real numbers, C the complex numbers, H the quaternions, and O is the octonions. So I'm going to combine the 4 division algebras, and I'm going to construct what I call, a real complexified quaternionic, octonionic value gravity as a grand unified field theory. So what I'm going to have is a pure gravitational theory, but I'm going to use the real numbers, the complex, the quaternions and octonions all combined, and I'm going to formulate a unification theory based on pure gravity, okay, but relying only on the 4 division algebras.
So can you just say for our viewers and for me, what is the, so we have, these are number systems like the reals, but they're also division algebras. So just a brief definition of a division algebra, and that helps us
Yes,
understand.
I'm going to
define division
yes,
algebra.
yes. So, so they apparently, you see in nature, you see the only 4 division algebras. I think it was Hurwitz who classified them, meaning that they don't have divisors of 0. So there are only 4 mathematical possibilities and no more than 4. There are the Sedenions, but the Sedenions are not really division algebras. So the fact that it's only 4 mathematical objects that you can construct, it may tie up with the fact that we only have 4 forces in nature. So there may be a deep connection between the existence of 4 division algebras and 4 forces in nature. So the motivation behind this is to see whether or not there's a true connection between the fact that there are 4 forces in nature. By that I mean the electromagnetism, the weak force, the strong force, and the gravitational force, and the fact that we only have the reals, the complex, the quaternions, and the octonions. So I'll be defining them. So this will appear in the Advances in Applied Clifford Algebras, the paper, very soon. Okay, so the contents, since I don't want to overwhelm you with too much stuff, I'm only going to concentrate on the key points here. So I'm going to talk a little bit about the Kaluza-Klein mechanism. In other words, how gravity in higher dimensions, when you compactify to lower dimensions, you can generate your electromagnetic force and your Young-Mills forces and your gravitational field. So this is the old traditional way of obtaining a unification from higher dimensions. But here, I'm only going to be working in 4 dimensions. I'm not going to be working in higher dimensions, only 4 dimensions. But what I'm going to do is I'm going to introduce the ingredient of the complex numbers, the quaternions and the octonions, that I'm going to mimic the role of higher dimensions. So I'm going to replace the role of higher dimensions, and I'm going to replace them by introducing these extra algebraic structures. Okay, so I'm going to introduce, what I mean by a real complex quaternion octonionic metric, and I'm going to tell you what the connection is, what the curvature is, and then I'm going to construct a gravitational theory based on these division algebras. And I'm going to tell you how you can embed the standard model into this complex quaternionic, octonionic gravitational theory. And then I'm going to tell you that the natural gauge group that arises from this construction is not 4 copies of SU3, but it's going to be 4 copies of SU4. You see, the 4 copies of SU3 are very nice, because when you have 4 copies of SU3, the rank of 4 copies of SU3 is 8, which coincides with the rank of E8. So the 4 copies of SU3 is, it's like a maximal compact subgroup of E8.
Does it have any relationship to the real Clifford algebra, CL16?
Yes, I will go. Yeah, I will go into this later. Yeah. And then, of course, I don't have time to talk a little bit about the correspondence with gravity in higher dimensions, but I'll say a little bit about U4, U4, and U16. Yeah, I'll say something briefly about that. But I'm only going to concentrate over here until this point, because I don't want to overwhelm you Also, I didn't have too much time to review the whole paper anyway, I'm sorry. But anyway, so let me just give you a very brief reminder of what the Kaluza-Klein idea was. So you see, the Kaluza-Klein idea was, let's start with a higher dimensional space beyond 4 dimensions. So I have 4 dimensions, which is the space that we perceive. And let's suppose that we live in higher dimensions. So you have this extra internal n-dimensional space. So now your space is like a product space of your base manifold, your base space-time, and n is your internal space. So the total dimension is 4 plus n internal dimensions. So let's suppose that you can rewrite the metric, in this higher dimensional space. You can decompose it into in this block form, where G mu nu, this is the standard metric that we'll see in 4 dimensions. And these extra pieces here are your gauge fields that we're going to see when we compactify. This object over here is like the metric in your internal space, the metric in your internal dimensions. The components look at scalar fields from the 4-dimensional point of view. So this is the decomposition of your metric in higher dimensions and how you're going to break it up into your components in lower dimensions. So the idea of the Kaluza-Klein compactification is that when you assume that your fields do not depend on the extra coordinates, so you can decompose your curvature in higher dimension into this form. So you have your ordinary curvature tensor in lower dimension, and you have the square of your Yang-Mills gauge fields. So the idea is, where do the gauge symmetries in lower dimensions come from? So your symmetries, your gauge symmetries, your Yang-Mills or your electromagnetic or your U1 in lower dimensions stem from the isometries of your internal space. So the isometries of your internal space are what generate your gauge symmetries in lower dimensions. Let me just go. Okay, so essentially you're going to have so many Killing vectors associated with your symmetry group of your internal space. And so the idea is that your gauge fields in they stem from the isometries of your internal space. So what happens is that when you write the curvature in higher dimension, when you break it up into pieces, you're going to have one piece which gives you the ordinary curvature of your space-time, and the internal components of your curvature are connected with your Yang-Mills gauge fields. And you have also here, this is the curvature in internal space. So from the 4-dimensional point of view, the components of this metric look at scalar fields. So what happens when you have a gravitational theory in higher dimension, really it furnishes a 4-dimensional theory of gravity, encoded by this curvature scalar, your Yang-Mills gauge fields, and a bunch of scalar fields. So from the mathematical point of view, this is what people call a nonlinear sigma model. So essentially what you have is that a gravitational theory in higher dimension, from the point of view of lower dimension, it looks like an ordinary gravity theory plus Yang-Mills plus a bunch of scalar fields. So what I'm going to do is I'm going to substitute this idea, and I'm going to now use my real numbers, my complex numbers, my quaternions and octonions, that are going to play the role of higher dimensions, but in reality I'm going to be working only in 4 dimensions. So I'm going to trade off the idea of higher dimensions, and I'm going to be playing with complex quaternions and octonionic numbers. So this is the idea, okay? Yeah. So, okay, so let's now talk about what do I mean by a complex quaternionic, octonionic object, Let's suppose that I start with an octonionic number. An octonionic number has a real piece, which is what I call the x sub 0, and a bunch of 7 imaginary components. Okay, so this is what an octonion looks like. I decompose a number into a real piece and 7 imaginary units. Okay, so that's the first line above. Now let's suppose that you pick up any of these components, the x sub 0, x1, x2, x7, and with a microscope you look at them, and then you realize that each component is itself made out of quaternions. Okay? So I'm going to say that each of these components is itself a quaternion. So this is the way I label my indices, is that the real part of my octonion is itself a quaternion. Okay? So I'm going to decompose my x big 0 here into the real part, the quaternionic real part, and my 3 elements of my quaternions. You see, the quaternions are 3 imaginary elements, Q1, Q2, Q3, and my real part of my quaternion. So I'm going to break each of the components of my octonion into quaternionic pieces, okay? And then I'm going to go further. I'm going to say that each of these components of the components of the components are themselves complex numbers. So now what I call them my x00 is itself a complex number, okay? So I take each of these and I break them into pieces. So this is what I mean by a complex quaternionic octonionic number, okay? So I start with an octonion, I look at each of the components, and then I break each octonionic component into a quaternionic piece, and then I look at each piece and I break it into a complex number. So this object here is very rich, as you can see, okay?
But L is going from 0 to 3 only.
I'm sorry. No. Okay, now my capital A, okay. Now this object here, I can rewrite it in this form. Of course, Qi, it should be here really. I have my real part of my quaternion, 1, 2, 3. I'd be here 4. I should erase this 4 over here. What I mean is the 0 is the real part of my quaternion, and my 3 imaginary elements is 1, 2, 3. Yeah, I should erase this 4. But my octonions, I have 7 imaginary units, 1 through 7, and the real part is the 0. Okay? So, yeah, so the I should go from 1, 2, 3, and 0. So, and then of course, each of the components is itself a complex number. So a condensed way to write this object is to write it in this form, where I'm going to have a double index notation. The capital I ranges from 0, 1, 2, 3, which tells me the quaternionic piece. And A ranges from 0, 1, 2, 3 until 7, which labels the octonionic component. And each component of X itself is a complex number. Okay, so this is a condensed way of writing a complex quaternionic octonionic number.
So okay. X is a 64-dimensional number.
In a way, yes. Yeah. So this is where why I'm going to have 4 copies of SU4. In a way, okay.
So can I say, Carlos, this is just like a 64 dimensions total, and it's.
Yeah, in a way, yes, because you have 4 times 8 is 32 times 2 is 64. Yes, yeah. In a certain way, it's like working with a 64-dimensional space. Yeah.
It makes me think of Tony's work on the 64, like the I-Ching and.
No, but I've been working also on Clifford 16. Yeah. Okay. Any questions about this? Yeah. Okay. So now I'm going to work a little bit about the algebraic structure. Okay. Okay. So let's look at the quaternions and the octonions. You see, by the index 0, I always refer to the real part of a quaternionic or an octonionic number. Okay, so let's look at the algebra of the quaternions. The algebra of quaternions, you're going to have 3 imaginary units, so that when you multiply them together, they are non-commutative. The quaternions do not commute. The octonions do not commute, and they are not associative. The quaternions do not commute, but they are associative. So when I have the product of 2 quaternions, I'm going to have this relationship over here, where the numbers ijk range from 1, 2, 3. This algebra really is nothing but the algebra of the Pauli 2x2 spin matrices. This is the Pauli, the SU2 spin algebra. The SU2 is the algebra of the weak interaction, really. The quaternions, the octonions is more complicated, because now you see I have an antisymmetric object, ABC. See, ABC is purely antisymmetric in its indices. But remember, ABC range from 1 to 7. here I have a rank 3 antisymmetric tensor. So the structure constants of the octonions is more complicated. Okay, so there are many ways in which can choose to define the structure constants of the octonions. So there are many choices that people make, you know. For example, Dyson in particular, you know, he chooses to be 1, the number 1, he associates to this combination of numbers. You know, when A, B, C is equal to 1, 2, 4 or 2, 3, 5, he assigns the number 1 to these 7 sets of combinations, you know, or cycles, you know. Another way you can represent these commutation relationships. You know, you're familiar with the Fano plane, where you have a triangle with 7 lines. You've seen it before, the idea, yeah. So what happens is that, well, since I'm here, let me just...
you can erase that right there.
Can I erase?
Yeah, you can erase all of that except for the nice writing.
Yeah, yeah. I can erase this for a second, you know.
Carlos, so you're going to explain the definition of division algebra later, you said?
Well, I'm starting right now with the definition. How do you define the algebra? In other words, how do you multiply these numbers together, essentially?
So
how do you multiply them?
So because you multiply them, that's why it's a division algebra.
Yeah, yes, and you want to make sure that you don't divide by 0, because when you divide by 0, you have problems. So you know, they're called division algebras because when you have, if something times something gives you 0, if A times B gives you 0, it means that A or B has to be 0, you know. There are many algebraic structures that give you A times B is equal to 0, and sometimes you could have the possibility that A or B are not 0. But in this case, if A times B gives you a 0, that means that either A or B has to be 0. That's where the name division algebra comes from.
So in this sense, when I look at the real numbers, and because ordinary arithmetic that is of that form that you said, and that's why I would call it an algebra. That normal elementary school division and multiplication, etc. That's the division algebra sense. And then you go to the complex numbers and you call that a division algebra because it has the same...
Yeah, because you can multiply if you multiply two complex numbers and if it gives you a 0, it means that one of the A or B has to be 0, you know. But then sometimes you could have algebraic structures where the products of two numbers which are not 0, maybe they can give you something which is 0. It happens with the split octonions or the Sedenions, for example. Yeah, go ahead.
So there is another important property of the division algebra here, which is that it is a norm algebra. So the norm of the product is the product of the norm, which is exactly like for the complex number. Yeah. So you can use polar coordinates, where each number have a size, which is its norm, and an angle. And to multiply them, you add the angle and you multiply the size. And that doesn't work with the Sedenion or non-division algebra.
Oh, that's right. I mean, I haven't defined the norm. You know, in order to define the norm, you take. Okay, I have to define what I mean by the complex conjugate. What the complex conjugate it is. But let me just look at the final plane. You know, for example, let's look at the final plane. Okay, so this is.
Did we get Todd, everybody?
Maybe you could just quickly review your definition for Todd.
For Todd.
Just the definition of the complex quaternionic octonion, just for Todd.
So I have to go.
Unless he's very familiar with it. Todd, he knows.
He knows what those three different things are, but he just doesn't know what you mean by the combination.
Yeah, we're taking it's a tensor product.
How the tensor product of the lower numbers can be used to build up to the larger levels.
Let me just go back briefly. By a complex quaternionic or tonionic element, I mean I start with an octonion and I decompose it into its real part and the 7 imaginary units. So and then I look at each of the components of this octonion, and they themselves can be broken up into their quaternionic numbers. And then each of these quaternionic numbers is itself a complex number. Okay, so I can rewrite a complex quaternionic or tonionic object I can rewrite it in this condensed notation, where the subscript I ranges from 0, 1, 2, 3, which it spans the quaternionic algebraic elements, and the A spans between 0, 1, and 7, which spans the octonionic algebraic elements, and each of these components, x itself is a complex number. So by a complex quaternionic octonionic, I means that. So is this clear? Can you hear me? Yeah.
He can hear you, but he can't see you.
He cannot see me.
No,
Yeah.
I guess so. You're saying I ranges from 0 to 4.
Yeah, actually, the 4 is a typo. It goes from 0 to 3.
Yeah.
It's a
0 to 3. Oh, that
Yeah.
makes more sense.
Yeah. You have the 3 quaternionic units and the real part of the quaternion, and the octonions go from 7 imaginary units to the real part. Okay. So this object here, this double index notation, tells me that I have when I take the tensor product of the quaternions times the octonions, so I span over the quaternions and octonions, and and the components themselves are complex numbers. Okay, so I have a complex.
Is this 28 dimensional?
No, it's 4 times 8, 64. It's 4 times 8 times 2, 64. It's a 64.
4 times 8 is 32. Right.
Yeah.
Times 2.
Times 2. Don't forget the complex number. It doubles.
Oh, its real dimension is 64.
Yes.
Okay.
Okay. So now I'm just describing, the multiplication rule of quaternions that essentially is isomorphic to the Pauli spin algebra, the SU2 algebra. When I take the product of 2 imaginary quaternionic units, you're going to have if they are equal to each other, squares to -1. We know that because I have 3 imaginary units. And when they are not equal to each other, then I have, this is the Pauli spin algebra as we're familiar with. The octonion multiplication is more subtle because now I have these antisymmetric structure constants, and now I have to choose how I define them. So this is how I can look at the Fano plane. The Fano plane is nice. It's a nice geometrical way of how you say, mnemotechnic, that allows you to
mnemonic.
Mnemonic, yes, to remember them. So let me look at, for example, let's suppose that I assign the combination when A, B, and C are equal to 1, 2, 4. The structure constant is given to 1. So I have I'm going to have a triangle. So let's assign 1 and 2. Okay, so I have a vertex 1 here, and I have the midpoint is 2. So the combination of 1, 2, and 4 gives me 1. So that means that the vertex 1, point 2, and point 3 are in the same line. Let's look, for example, 2, 3, 5. Now let's look at 4. 3, 4, 6. Okay, so let's have 3, 4, 6. Okay, let's suppose. Okay, let's have 3, 4, 6 gives me another line. Okay, and then what I have 6, 1, 5. 5, 6, 1. Okay, 6, 1, 5. Yeah, well, anyway, maybe the order. So the bottom line is that each triplet of numbers, they belong to a line. So I have 7 lines. 1 line here, 1 line here, 1 line here. Then I have another line here, another line here, and another line here. And then, of course, you have to include this line here, the circle. So I'm going to have 7 lines. And I'm going to have 3 points in each line. And the ordering will give me 1 or -1, depending on the permutation. Okay? So this is the convention. So I assign 7 sets of index triplets. It's like having 7 ways where you can embed the quaternionic algebra into an octonion algebra. Essentially, each of these cycles represents a quaternionic subalgebra embedded in the octonions, And the convention is arbitrary. There are many ways that you can define it, The important thing is that you have to be consistent with the ordering, because these numbers do not commute, and the algebra is not associative. So you have to, you have to choose a mnemonic way of doing. Yeah.
There's another interesting mnemonic, which is if you take these axes of symmetry of the tetrahedron. So you have 7 axes of symmetry that run through a shared centroid point. So each of the 7 axes of symmetry of the tetrahedron has 3 points, right? The center point at the centroid of the tetrahedron, which is the center of all 7 axes. So you have that. You have a 3-dimensional mnemonic in the.
Well, the Sedenions, actually, you can think of the Sedenions. In other words, the quaternions uses this plane. The tetrahedron will be associated with the Sedenions. So the algebra of Sedenions is connected to the points on the tetrahedron. Yeah. So,
but it's impossible to get the same consisting way, so that each face is an octonion. Yes.
You can, in a very pedestrian way, you can visualize the Sedenions. You play with the quaternion, with the tetrahedra and the Sedenions, in the same way that I'm playing here with an equilateral triangle and the octonions. Okay, so anyway, okay, so but you get the gist of my idea. Let me see if I can find the combination that gives me the little circle here. Do I have a 2, 6?
Yes, 7.
I'm sorry?
7, the 7 at the bottom.
7. Okay. So that means that 2 with 7 has to give me a 6 somewhere. Yeah, because I have a 6, 7, 2 here. 6, 7, 2 combination. So that means that I must have a 6, 7, 2. 6 times 7 gives me a 2. So the ordering is very important, whether you go clockwise or anti-clockwise, because if you reverse the order, you change the minus sign in the multiplication. But you get the gist, Now I have to tell you, how do I take the complex conjugation? I know when you have a complex number, like x plus iy, when you take the complex conjugate, you just reverse the sign of I. So the complex conjugate of x plus iy is x minus iy. Here, the complex conjugation is that you reverse each imaginary unit, you change its sign. So in the complex numbers, we reverse I to minus I. With the quaternions, each imaginary unit, you change the sign. And with the octonions, each imaginary unit, you change the sign. So this is what I mean by complex quaternionic octonionic conjugation. You just reverse the sign. Here I wrote the metric, but I should write the metric later. Anyway. Okay, is this more or less clear? And then, like Ray was saying, when you take the norm of an octonion, for example, you take a capital X, you multiply by its octonionic conjugate, and that should give you the norm, and you take the square root, You take X, you take a complex conjugate, and you take the square root, and that will give you the norm of your octonion. With the quaternion, it's the same way. You take the quaternionic number, you multiply by its quaternionic conjugate, and then you take the square root and you get the norm of your quaternion. Like you do with a complex number. You take a complex number, you multiply by its complex conjugate, and you take the square root and you get the norm. So here is the same thing. You get the norm in this way. Okay, so now I'm going to tell you, so how am I going to construct a gravitational theory whose metric components are real complex quaternion octonionic value? Okay, so I'm going to. So what I'm going to do is I'm going to start with this. I write it in bold font here to let you know that this object here is a real complex quaternion octonionic value. Okay, so what I'm going to do, I'm going to break it. I'm going to extract the real part, the R component. I'm going to extract it, and I'm going to separate it from the rest. Okay. So I'm going to have like an internal part of the metric, and I'm going to have an external part of the metric. The external part of the metric is related to ordinary gravity, and the internal components will be related to your Yang-Mills gauge fields. In other words, your SU3, SU2, U1 gauge fields will live in the internal, will be encoded in the internal components of your complex quaternion autonomic metric, and the real gravity, the Einstein gravity, is encoded in the real part here. Yes.
You have not defined what is the conjugate of tensor.
Yeah, I will. I will. Yeah. Okay, I'm going to define it now. Yeah. Okay. Okay. So now remember my index notation. Capital I spans from the real quaternionic and the 3 imaginary quaternionic units. Capital A spans from my real octonionic unit and the 7 imaginary units. And each number itself, each component is imaginary. Okay. Okay. Now by conjugation, I means this is what I'm going to tell you. You're going to reverse the imaginary units by the opposite. So by conjugation, I mean full conjugation, and they're complex, quaternionic, and octonionic conjugation. So the bar means full conjugation, the full combination. Okay, because remember, each of these components, okay, this is real, but if you look at one of the, let's look at the 0, 0 component here. It's going to be itself an imaginary, a complex number. So it has a real part and an imaginary part. This component here has a real part and an imaginary part, and so forth. Now, because I'm going to define this operation, because remember, in ordinary relativity, we know that the metric is symmetric. When you replace mu for nu, we know that it's symmetric. Here, the notion of symmetry is going to be replaced by this condition, that the full conjugation is given by just reversing the order of my indices. Like okay. Yes, this is some sort of hermiticity condition on your metric. Yeah. So notice, and yeah.
The G mu nu, which is the complex quaternionic, octonionic, has actually a real part. Is that redundant with the first G mu, or is it?
Yeah, but here, you're right. Here, I'm doubling, yeah, because in reality, if you look at this decomposition, and really, I have a bimetric theory. You probably heard about these bimetric theories of gravity. I have really two metrics, you know. I have a metric that lives here in my real part, and I have another a real metric that lives inside this object here. You're right, because look here, I have a G mu nu here, which is symmetric, and it has a 0, 0. So here I have a G mu nu, and here I have a G mu nu with an extra pair of indices. So in reality, I do have two metrics. This is a bimetric theory. Yes. And by conjugation, that means when you take the conjugation, you take I to minus I to minus I to minus I, and you do the same thing with the quaternionic elements. You reverse the sign. Okay, that's what I mean by full complex. Full conjugation. Yes.
So I was following you through the algebraic or the mathematical part in general, but then when you got to this slide and you just put on physical, values as gravity, and you wrote that, that expression at the top, I can assume that you're basically taking some known gauge symmetry that relates these physical quantities and then finding the same form in this.
I'm going to use the algebra itself to deduce what the gauge symmetries are going to be. Okay. So I start from the quaternion octonionic complex, the algebra acting on itself, like Dyson and Cole did, and from the algebraic structure of the quaternions, octonions, I'm going to infer the standard model, the gauge symmetries. Okay. So this comes first, and the SU3, SU2 comes afterwards. Okay. Yeah. Let me see. Any more questions about this? Of course, it's always good to work with a condensed notation, because but the important thing is that you know what each index means, So now let's suppose that, okay, now let's look at how do I take a line element in this complex quaternion gravity. Remember, a line element has to, I want to get something which is a real number. You know, I cannot get a complex number or an octonionic number. So what you do is you take the product, and then you take this bracket operation. It means that you take the real part, and this is where the two metrics come. Okay, this is this is ordinary metric of gravity, and this is the other metric that comes from the real part of the complex quaternions and octonions comes from here. So it's like having a bimetric theory of gravity in a certain way. So now you see, octonionic gravity was actually started by the Brazilians. You know, Professor Oliveira in Sao Paulo, and his student, her name is Shirley, but in reality, you see what happens, the parents of, she's a woman, what happens, the parents in Minas Gerais, they loved Shirley Temple so much, so when they baptized her and they gave her the name, they had a spelling mistake. So instead of writing Shirley Marquez, they wrote Shirley Marquez. So
which means in English, surly, very spicy.
Yes. So her name is Shirley, but in reality she's a woman, and she's actually in Austin now. She wrote a very nice book about consciousness. You know, she's a very smart Brazilian woman. Anyway, so like I say, they did work with octonionic gravity many years ago. So they were one of the, of course, Borchenius, and I remember Einstein also was interested in antisymmetric gravity, playing with a complex metric, antisymmetric metric. But actually, the Brazilians were the ones who pushed this idea further, as far as I know. Anyway, so by this operation, that means you take the real part. So you do have, you're right, like Richard said, you have two metrics here. The people who work in dark matter, do they have also these bimetric theories of gravities? In Daniel, you heard about people who work with two metrics?
There are people who are doing dark matter from the bimetric theory, not the other way around.
No, the other way around.
So there are people in dark matter who are going to the bimetric theory, but the other way around. Because usually people who are looking at this type of gravities are looking into unification of forces, and they need to explain dark matter and dark energy also.
Okay, so
I'm not aware of any working theory so far.
Okay, so remember, in gravity, you know, I need to tell you how to parallel transport vectors in this geometry. So I need to tell you what the connection looks like, okay? So I'm going to construct the connection, okay? So the connection or affinity is called, it's going to have an external part, which is a pure gravitational part, and the internal part. So I'm going to choose, okay, remember this theory is actually much richer than, I'm going to choose for my affinity tensor to have this form. And you will see that this gauge field is the one that encodes the SU3, SU2, U1. So I'm going to choose a particular connection in this form. This is the ordinary, you know, Riemann-Christoffel symbols. And my internal part of my connection, I'm going to choose it to be of this form. Okay? And remember, in the Palatini formulation of gravity, you choose the connection to be independent of the metric. You know, this is the way that Palatini chose it. Of course, when you perform a variation of the action and you solve for the metric, you can choose. You can find out that the ordinary Christoffel connection can be given as derivatives of the ordinary metric. But in this case, this internal part of the connection is independent of the metric. Okay, I'm going to choose it to be independent of the metric. Now the ordinary part of the connection, I'm going to choose it to be given by the torsionless Levi-Civita connection. You know, just to make life easier. But in general, you could work with more general connections than this. Remember, I had decided to choose a very specific choice for my connection. But in reality, my connection has many, many components. This object here has many, many components. But in order to simplify life and to make connection with the standard model, I'm going to choose my internal part of the connection to be given by this object over here. So in other words, my gauge fields, my Young-Mills gauge fields, They live inside my internal part of the connection. They live inside here. Okay? So then, of course, I can decompose this bold gauge field into the quaternionic, octonionic pieces. Okay, because this has the real quaternionic part, a real octonionic part. Here it has an imaginary quaternionic part and an imaginary octonionic part. Here I have a real quaternionic part and an imaginary quaternionic part and a real octonionic part, and vice versa. Here I have a real quaternionic part and an imaginary. So I'm looking at all the possible combinations that I can have, because after all I'm taking this tensor product, okay? So now what I'm going to do is I'm going to write down, okay, you see the internal part of the connection, I take it to be independent of the metric, like the Palatini formalism. And my ordinary part of the connection is just given by the Levi-Civita torsionless connection. Okay, so I'm going now to compute the curvature. You know, I have a connection, now I'm going to compute the curvature. So the curvature is going to be a very rich object. So this bold face font is going to have my ordinary curvature tensor. I'm going to have an extra piece here. So the internal part is what contains the gauge fields, my gauge field strength, my field strength tensor. Okay, so my SU3, SU2, U1 field strengths live inside here. They live inside this curvature. You know, they live inside the internal part of my curvature tensor. Okay. Okay, so then when I do the algebra, you know, I can rewrite this object in this form, and then this is my connection, and now I'm going to have 32 complex valued gauge fields, or 64 real value gauge fields.
So there is no any coupling between this internal part and this.
I'm sorry?
There is no any coupling or any interactions or any mixing terms between this internal.
Oh yeah, oh yes, they are mixing. I mean, well, the external decouples from the internal, but among the internal, there's going to be a lot of mixing.
So in that case, yes. is your connection right now is locally Lorentz invariant or?
Yes.
Still Lorentz, even so this mixing will go to zero when we take it locally, right?
Well, there's going to be when I'm going to write down the components of your field strength, and there's going to be mixing. Yes. But the space-time part is going to be decouples from the rest. But the internal part is all mixed together. It's all this soup, all jumbled up together. So I need to disentangle it later. Yes. Yeah. Okay. So now how do I? Okay. So my gauge field is going to have all these components. Remember, mu is my space-time index. It ranges from 0, 1 to 3. But my internal index, you know, you have all these components, you know. Now, how do you take a commutator of a tensor product? Remember, here, this is my quaternionic algebra, the generators of my quaternionic algebra. The EAs are the generators of my octonionic algebra. So how do you take the commutator of a tensor product, okay? So I have to define for you how do I take the commutator of a tensor product. Because I show you how to take the commutator of two quaternions, how to take the commutator of two octonions. But here I have a tensor product. So there's going to be mixing, okay? So this is defined, when you take the commutator, this is defined by this expression. In other words, the commutator of the tensor product is given by this formula over here, okay? So I'm going to have an anti-commutator, commutator, anti-commutator. Okay, so I'm going to have both commutator and anti-commutators. So in a certain way, supersymmetry is already present here in a way, because supersymmetry deals with anti-commutators and commutators.
So how do we? What about the property of non-associative of octonions?
Well, non-associativity will come when you want to build actions. Because then when you're going to multiply three objects together, you have to be very careful in which order, how you multiply them, because due to the non-associativity, when you have three objects, when you want to multiply them together, when you have octonions, then it's ill-defined. You have to define how you perform the multiplication. Yes. Okay. So now what I'm going to do is I'm going to evaluate the components, each of the components associated with this master field strength. I'm going to write now the specific components associated with this complex quaternionic or quaternionic field strength. Okay, I'm going to write components, each component by component. Okay, so I'm going to have, you see, the 0, 0 part is given by this expression. So this looks like electromagnetism, like a U1 gauge field. If you throw away the 0, 0 subscript, forget about the 0, 0 superscript, and if you just focus on the structure, this looks like a U1 gauge field strength. Okay. Now you're going to have this combination between the real quaternionic part and the imaginary octonionic part. So you're going to have mixing. Okay. Here, these are the structure constants of your quaternions, and these are the structure constants of my octonions. Okay. But let's focus, for example. Okay. So this looks like a U1 gauge field strength, like in electromagnetism. Now let's look at this part over here. Remember, my K is my imaginary quaternionic components, and it ranges between 1, 2, and 3. The 0 over here is my real part of my octonions. So if you look at this object here, this object here, and this object here by itself, okay, forget this. Just look at this piece here, and this piece here. It looks like an SU2 Yang-Mills field, because these are the structure constants of my quaternions, which is isomorphic to the SU2 Yang-Mills structure constant. So this object over here encodes an SU2 Yang-Mills field. Okay, and then the other components, this object over here, and this object over here, will contain my SU3 components. Okay, so I'm going to be able to. I'll let Ray look at them.
It will be a G2, no?
Yeah. Well, G2 is the automorphism group of the octonion. It's actually more complicated than that. But what I'm going to say is that out of these 32 complex valued field strengths, 1, 2, 3 sets, my Yang-Mills, my U1, okay, is encoded in the 0, 0 part. And then my SU2 is encoded in this combination. Now I'm going to tell you where the SU3 piece lives. So you probably remember that the first of the exceptional groups, G2, this is a rank 2 Lie group. It has 14 generators. This is the automorphism group of the octonions. Okay. So you're going to have this chain of subgroups. SO8 contains SO7, contains G2 and SU3. SU3 lives inside G2, And if you probably remember the difference between a round 7-sphere and a squash 7-sphere. The round 7-sphere is given by this coset, SO8 over SO7. This is the round 7-sphere. The squash 7-sphere is given by this coset, for example. Anyway, so this reflects how the SU3 group is embedded into. So I'm going to have 7 plus 21. Let me just go back here. I'm going to have. Let me just go back here. Okay, I'm going to have here 7. 3 times 7 is 21. Because remember, C ranges between 1, 2, and 3. K is between 1, 2, and 3. C is between 1, 2, and 3, and 7. So 3 times 7 is 21. Here I have 7. 21 plus 7 is 28. So essentially I have 28 objects. And remember, 28 is the dimension of SO8. Okay? So in this way, this is how I'm going to embed SU3 into these two field strengths. Okay. So my SU3 Yang-Mills can be embedded. Okay. So this is my SU3 has 8 generators, 8 gluons, and then I'm going to embed them into this combination. Okay. So in a certain way, what I have done is I have embedded my SU3, my SU2, my U1 inside this internal connection in this space involving the quaternions, octonions, complex numbers. Okay, I'll let you digest this for a little bit, because now I'm going to go into the details of the algebra. This is a very hand-waving explanation of how to explain where each part, how you can embed this part here, how this chunk can be embedded here, how this chunk can be embedded here, just to give you an idea of where each part, how to visualize the embedding of SU3, SU2, and U1. Ali, so does this make any sense? Yeah? Anyway, let me have a little bit of water. Yeah. Okay, so now I have given you more or less like a hand-waving explanation how this SU3, SU2, and U1 are embedded. I'm going to give you a more algebraic, more rigorous definition of how the algebraic structure emerges. So Richard may like this because this is related to Clifford algebras, you know. Okay, so let me just go to this point. We know that the complex quaternionic algebra is isomorphic to the Pauli spin algebra, which is given by 2 times 2 complex matrices. Now, this is where the notion of associativity comes into play. You see, because the octonions are not associative, you have to be careful. What do you mean by the left action or the right action? Okay, so the left action of the octonionic algebra on itself, okay, or the right action of the octonionic algebra on itself can be represented by 8 times 8 matrices. Okay, the symbol L here means is that I'm taking the left action. Okay, you could take the right action if you want, but this is what L means. You're taking the left action. Remember, because the octonions, because they are non-associative, you cannot represent the octonionic algebra in terms of matrices, because we know that matrices are associative. They don't commute, but they are associative. So you cannot represent an octonion by a matrix. However, you can represent the left action of an octonion on itself, or the right action on an octonion in itself by a matrix. That you can do. This is what Dyson did, and this is what Cole did. Okay, so essentially, the left action of the octonion algebra on itself can be represented by 8 times 8 matrices. So now I'm going to have my 32 generators, which are complex, can be represented by 32 complex 16 by 16 matrices, or 64 real 16 by 16 matrices. Why? Because remember, when you take the tensor product of 2 matrices, remember, if this is a 2 by 2 matrix, and if this is an 8 by 8 matrix, when you take the tensor product, you will have a 16 by 16 matrix. Okay? So let me repeat that. The Q's, imagine, are given by 2 by 2 complex matrices. The A's are given by 8 by 8 matrices. When you take the tensor product, you end up with 16 by 16 matrices. You know, how do you take a tensor product of a matrix with another matrix? What you do is you take each entry of the first matrix and you replace it by the whole matrix of the second matrix. You go to another entry of your matrix and you replace that by the whole matrix of your second matrix. So in this way, this is why the tensor product of a 2 by 2 with an 8 by 8 is a 16 by 16. Okay, is this clear? This is very important. This is where the 16 by 16 comes into being. And of course, they are complex because you remember I have a complex. The complex numbers appear also in this description. So essentially, is that that 64 is the real dimension. You know, remember, 2 is the complex numbers, 4 is the quaternions, 8 is the octonions when you multiply them. 64 is the real dimension of this algebra. Okay. So this now I'm going to tell you where these groups appear. Okay. So remember, each complex system by 16 matrix can be expanded in terms of a complex Clifford algebra. You know, you can do it this way because this complex Clifford algebra, remember, it's 2 to the 8 is 256, right? 2 to the 8 is 256. And 256 is the same thing as 16 times 16. This is what Tony, right? But however, remember, but here I had 32 complex generators. Here I have 256 complex generators. So this algebra is way too large. So what I'm going to do is I'm going to expand. It's much easier to expand the 32 complex 16 matrices in terms of the tensor product of the elements of a Clifford, a complex Clifford 5 algebra, and this is the unit 4x4 matrix. It's much easier to make the expansion in terms of this tensor product of a Clifford algebra, a CL5 complex, and this is the identity matrix, than a Clifford A, because Clifford A is way too large, you know, okay? So remember, a Clifford algebra, a CL5 has 32 generators, but if the algebra is complexified, you double that and you have 64 generators, okay? So the idea is that I'm going to represent those 32 complex 16 by 16 matrices. I'm going to expand it in a basis of CL5 Clifford 5 algebra and my unit element. Okay, so let me just, Richard's probably more familiar with this. Let me just remind you the isomorphisms between real and complex Clifford algebra. You see, when you have a complex Clifford algebra in these odd dimensions, because it's complexified, you can break it up into two pieces. And each complex algebra is itself isomorphic to a matrix algebra comprised of 2 to the m times 2 to the m matrices. So essentially, at the end of the day, you can show that the complexified Clifford 5 algebra is essentially 2 copies of a complex CL4, and each CL4 can be broken into 2 U4s. Because remember, this has 16 plus 16 plus 16 plus 16 gives me 64. And 64 is the dimension of CL5, because it's 2 to the 5 is 32. Because it's complex, I double that, I get 64. And remember that this is what I precisely need, because now I have here, I have 4 times 8 is 32 complex. It's like 64, 16 meters. So therefore, I'm going to expand these algebraic generators in terms of 16 times 16 matrices. Okay? So what I have done is rewrite this algebra in terms of Clifford algebras. That's what I'm doing essentially. You know, and so essentially, this my algebra really is in a U4, U4, U4. So this is where the 4 copies of SU4 come into being. Okay, so consequently, this algebraic structure of my complex quaternions and the left action of the octonions on itself, by virtue of this decomposition, you know, so I'm going to have an SU4, SU4, SU4 living inside 4 copies of U4. Okay, so what do I mean now my unification group? Yes?
Can you just give us a little more detail on how CL4 is U4, U4?
CL4 has 2 to the 4 is 16 generators. Yes, yes. And the algebra, so the algebra of U4 can be written in terms of Clifford 4 generators, because they have the same number of generators, and they are given, CL4 is given by 4 by 4 complex matrices. Yeah, so that's where it comes from. Yeah. Now, okay, so I'm going to have, you probably heard about this gauge group the SU3, SU3, SU3. Let me just show you. This is the ordinary gauge group of the strong interaction. This is the color group, okay? This SU3 is if there are 3 families of fermions, this is the family unification group. SU3 is the left chiral symmetry, you know, and SU3 right is the right chiral symmetry. So remember, this gauge group actually, it has rank 2 plus 2 is 4, 6. This is a rank 8 group. It's actually a subgroup. This is the maximal rank 8 subgroup of E8. Okay, 4 copies of SU3 is the maximal rank subgroup of E8. But in my case, this algebraic structure is actually richer because you can actually construct a grand unification model based on SU4. Because remember, SU4 contains SU3 here. And now instead of having 3 families of fermions, I'm going to have 4 families. Okay? Instead of having an SU3 left, I'm going to have an SU4 chiral left. So essentially, this group is the natural extension of this group. Okay? Okay. Well, remember, the Clifford algebra has 16 generators. If you look at the tetrahedron, it has 4 vertices, right? It has 4 faces, right? It has 6 edges, and it has a centroid, right? And it also has a bulk volume. So when you add everything together, you get 16. Yeah.
But the way maybe the same thing, but the way we're talking about it is you can take a face and relate that to a subpart of the A2 lattice in algebra, where you can get one of the groups, and then you've got the other groups. So you've got your SU2, SU3, and SO1, right? All represented in the D3 lattice, which is really what the tetrahedron kind of embeds all of those parts. Just it's a small tetrahedron is a very, very small section of D3 equals A3.
Yeah, the level of the root system. So S4 is A3.
Yes.
Which is equal to D3.
Yeah. Okay. So here, when you were in the rest, what I was saying is that this group structure is the natural extension of this group structure, where you have the SU3 of your color, your strong force. You have 3 families of fermions. This is the family unification group that rotates the families among each other. This is the left chiral symmetry, and this is the right chiral symmetry. So this is the maximal rank 8 subgroup of E8. So 4 copies of SU3 are natural. This is the maximal rank 8 subgroup of E8. Remember, E8 has rank 8. The Cartan subalgebra has 8 generators. So SU3 has rank 2 because you have 4 copies of SU3. This has 2 plus 2 plus 2 plus 2. It has 8, the rank of it. So this is not called a trinification. The trinification, this is an extended trinification. But the interesting thing is that this algebraic structure encodes this group, which is the natural extension of SU3 cross SU3, and E8 lives. This is a subgroup of E8. Okay, so the important thing is that now I'm going to have an SU4 color symmetry, right? I'm going to have an extension of color. You're going to have red, blue, green, and what color are the color you want to choose? Red, blue, green. You have to add an extra color. I don't know, whatever color you want to add. What is your favorite color? Then you're going to have 4 families of fermions, and then you're going to have this left, right chiral symmetry. So I'm going to tell you what kind of particles I'm going to have in this extended unification model. But remember, the algebraic structure emerges from the complex quaternions octonions. Remember, you start from here, and then you can derive this. It's not the other way around. Okay. So what I'm saying is the standard model fermions can be embedded into this fermionic matter belonging to these representations. So remember, this is the standard model quark. It can be embedded in capital Q. Okay, this symbol means I have a representation of 4 colors. 4 here is 4 families of fermions. I have a left chiral symmetry, and then it's a singlet, and the right transformation. And then the antiparticle, the anti-quark, you just look at the complex conjugate representation, which is given by 4 bar, and then you switch. And my leptons is the same. I'm just going to write them. This is probably better to write them like this. You see, in this SU4 extended model, remember the ordinary quarks that we're familiar with for the first family is I have the up quark and the down quark. I have the red, blue, and green. The down quark comes in red, blue, and green color. So the standard model has only this portion over here. This is the first family of the up and down quark. And they come in 3 colors, red, blue, and green. But since I have extended my SU3 to my SU4, I have I have more fermions. So I need to fill in the slots. So I'm going to have an extra quark that will be associated with my 4th color. 1, 2, 3, red, blue, green, and then which color, whatever, white, whatever color you want to choose. My down quark, my red, blue, green, is going to have an extra quark, carrying the extra 4th color. And because I'm enlarging my right chiral symmetry, instead of having an SU2 doublet, up and down, an SU2 doublet, I'm going to have an SU quartet, right? I'm going to have an up, down, and then the quark station of my up quark and my extend. So I'm going to have extra quarks, okay? Okay, and then when you take the complex conjugate, this is, okay, 1 here means the first family. I'm going to have 4 families. These quarks are going to come in 4 copies because I'm going to have 4 families. So instead of having the up and down, the charred and the strange and the top bottom quark, I'm going to have an extra family of quarks. And you can call it, I don't know, whatever name you want to call it, you know. Then the antiparticles are going to be given by this configuration, where the bar up, this means this is the up anti-quark, and it carries the anti-red color, okay? So this is the charge means the charge conjugation. So this is the up anti-quark, is the antiparticle, and it carries the anti-red color. so therefore, here I have the standard anti-quarks of the standard model, but I need to fill in the slots with extra quarks, okay? And what happens to my leptons? With my leptons, I'm going to have something very similar, because in addition to the ordinary neutrino, electron, you know, the mu neutrino and the antiparticles, I'm going to have extra leptons. I'm going to have an extra charge version of an electron, and I'm going to have the neutral leptons, okay? So I'm going to have, for the first family, I'm going to have my neutrino, my electron. I have a neutral partner of my neutrino, and I'm going to have a heavy version of my electron, okay?
That's the new part.
That's it, yeah, and also the neutrino, the heavy part, yeah. The capital N and capital E are the new particles.
We can call that the Carlito and the anti-Carlito.
I don't know. So since so I don't know, people who work in dark matter are looking for dark matter candidates may think of these extra leptons. And, yeah.
So, but first, let's clarify something. When you say you have new, like on top of the standard model.
Yeah.
From what I see now, you're basically, when you're referring to the standard model, you're still including standard model plus neutrinos, the light ones.
Yes, I assume assuming that the neutrino is massive. Yes.
Oh, yes. No, you first assume that the neutrino, like the light ones, the very light ones, the ones that we know, the ordinary leptons, are already in the standard model.
Yes, these ones. Yeah, these ones.
So you're already having a correction of the standard
a
model.
Modified standard model.
Oh yeah, because the gauge group, instead of being SU3, SU2, U1, I have SU4, 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 SU4.
So from your extension to the standard model, which is like the SU4, you're basically giving a more massive neutrino, which is perfect for dark matter. But I mean, again, you have to constrain the mass to be in the range that we're interested in, and a heavier electron. Yeah. Is that correct? So like
here you have an extra
fermions.
An extra electron, yeah. Yes.
So too much heavier fermions altogether.
Yeah, I would assume. Yeah, I would assume. Yes.
Any way of constraining the mass even?
But then I have to do. Then I have to do a full-fledged. I have to introduce matter. In other words, remember, I was looking at the algebraic structure. Now I'm trying to accommodate new particles. But you're right. I have to construct a phenomenological model. I have to have a Lagrangian. I have to look at how the symmetry is broken down, and then I have to look at do a quantum field theory. I have to look at the loop corrections, and then I have to look at the mass spectrum. I have to do a full-fledged, hardcore phenomenology. Yeah. So the particle physicists are the ones. I have to look in the literature to see. I'm sure there's models with SU4, because the literature is filled with infinite combinations of grand unification models.
And the contribution from this extension in algebra is giving basically just to the fermions.
Yeah. Well, yeah, and remember, don't forget the quarks also. I have my.
Right. So you have extra degrees of freedom, not just for fermions.
But also quarks.
But the quarks are fermions.
Well,
no, I mean no bosonic component.
Yeah, but the quarks, remember, they are bound, they are confined.
So
they are confined. Yeah, but.
So you can. I'm trying to clarify. So you have from the leptons more massive fermions.
Yes.
Massive 4. But because you have extra quarks and because you have extra degrees of freedom, do you have extra stuff for the bosonic components and other stuff, or just?
For the bosonic sector, well, I haven't introduced the scalar fields yet. I haven't introduced the Higgs field, for example. I haven't.
So it may be a difference there.
Yes, because remember, I have a bimetric. But I haven't introduced scalar fields. No, I haven't introduced Higgs fields yet. No, I haven't done that.
So you don't know?
I don't know. Because of course the Higgs sector, when you introduce the Higgs field, it has to fit the SU4 representation. So I haven't introduced the Higgs. No. I haven't introduced scalars. I only have this bimetric and this fermions. Yeah. Okay, can I proceed? Yeah. Let me see. Okay, this is okay. So I have extra leptons, and then so to conclude what I have just said is that the algebraic structure of this complex quaternionic and the left action of octonions led to this group structure, and reduced the possibility of extending the standard model by introducing. Oh, remember, I have extra gauge bosons. Remember, I do have extra gauge boson, of course. And then I have heavy quarks and I also have a fourth family of fermions. So I have a lot of extra stuff. But remember, the key to all of this is that it all stems from the algebraic structure of your division algebras. The algebraic structure could be your starting point, and from there you can move forward. So
are there group structure for this algebraic structure?
Yeah, I mean then you can see how do I break SU4 to SU3, SU2, U1.
No, but like the 4 SU4, you can think like a maximal subgroup.
Then you could see, I'm sure you can embed SU4. Well, I'm going to see how the...
But that structure, CHO, don't give a...
This gives you SU4, 4 copies of SU4. Yeah, it's like
SU13?
No, No. Here I don't have time for this, but let me just give you something. Something with the 16 by 16. Let me just give you something that I did with 16 by 16. Let me see if I can find it. Okay. Remember that I have U4. In reality, 4 copies of a U4 really are embedded in U16. So U16 is actually even more fundamental. I didn't have time to say that. Remember, U16 means you have rank 16. And remember, in string theory, remember when you look at the heterotic string, remember the heterotic string have a normally free group, 2 copies of E8. This is rank 8 is 16. And also another rank 16 group is the SO32. And so you do have a new U16 containing U4, because I didn't have time to explain how do I get U16 from here, but maybe in another lecture I could explain how they use 16. But the bottom line is that, remember the SU4 was a little bit too large to live inside the E8. But nevertheless, it lives inside E8 plus E8. Anyway, so this is a rank 16, and which you get in string theory. And this is where Tony is so excited about the Clifford 16, you know. And then, of course, you have non-symmetric Karusa-Klein theory. I didn't have time for that. But let me just give you the...
I will say that because E8 you can see in the Jinka diagram, the SU3, 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 SU3.
Ah, well, when you look at it, yeah,
if you, go to
you can take pieces, yeah, you can...
If you go to U16, so you have one more...
Yeah, you have one more node. You have one more node.
One more SU4.
Yeah, yeah, SU4 is rank, SU4 is rank 3. U4 is rank 4, SU4 is rank 3. Yeah. You have 3 nodes. SU4 has 3 nodes in the Dynkin diagram. Here, anyway, I was talking about E8, SO30, but let me just conclusion. Let me see. E12. Anyway. So okay. So let me just summarize what I said is that we have explored that this algebraic structure is very deep, and it leads to this SU4, and from there we can have an extension of the standard model by having an extra family of fermions, extra quarks, extra leptons, extra gauge bosons, an extra metric, you know. And then, of course, you can work with exceptional Jordan algebras. I didn't have time for that. In another lecture, I can talk a little bit about. But the bottom line is, this is a key point. Do the nature's 4 forces, are they really, do they exist because we have 4 division algebras? So this is the Platonic world that you are so excited about, the mathematical world, the world of ideas, maybe nature. In other words, if I were nature, I will use the quaternions, complex numbers, real numbers, and the octonions, because the mathematics will force me to do it. Because these 4 division algebras are so unique, if I were nature, I will use them. That will be to optimize
some sort of economy, some definition of economy.
Yes. If I were nature, why not? Out of all the possible choices, the most natural choice will be to use if I were nature, you know. I'm only a part of nature, but anyway. So I hope. Anyway, so let me give some reference. You see, this idea that the octonions could be connected to explain the standard model was really by Gursey from Turkey. He's the one who started this idea of playing with octonions. Kubo and Dyson, Jeffrey Dyson, I went to see him. I stayed with him and his wife a couple of days. And then Cole used the work of Jeffrey to explain the standard model from an algebra, you know. And then there's Searle, the Brazilians. You see, but look, 1985. Many years ago in Sao Paulo. Maybe I'll have Shirley come and visit you guys, the Brazilian. You know, she's in Austin, you know, at the Relativity Group. She's very nice.
Where is Sao Paulo?
Sao Paulo at USP.
Yeah, that's my home.
Yeah, I was in USP for 1 month. Many years ago, I was in USP for 1 month, you know.
That's where I went to school.
Yeah, oh, that's a great university. Yeah. Yeah, it's really very good university. Yeah, yeah. They have, yeah, because they have a very good mathematics institute and physics, and they have a very nice library, you know, and a lot of Russian scientists. But now you have La Universidad Paulista, and then also they have a Center for Theoretical Physics, which is the version of Trieste. They open a new, you know, so it's, no, Sao Paulo is a very active place.
So I want to ask you a question. So if I have 7 plus 1 integral octonions, with one being 0 and the other being the rest of the integral octonions, and then if I can associate my root vectors of the E8 lattice with integral octonions, okay, which Tony explains how, okay, so associate the root vectors with the integral octonions, right? Now, now,
because Ray is very good. Okay, go ahead.
Now, I transform my unit root vectors. So I'm essentially transforming this integral octonionic structure, and I transform it along some special angle, which is the one that generates the Elser-Sloan quasicrystal. If you project it to 4D, and that same angle would generate an H3 symmetric quasicrystal in 3 dimensions. But now, instead of having my integral octonions represented by root vectors of unit length, now I have transformed all possible root vectors that were trapped in my projection window to 7 plus 1 values, where one value compresses under projection to 0, and the other 7 compress under projection to Dirichlet integers. So what you have is you have these 8 values that used to be in one form in E8 that under transformation now have this 7 plus 1 transformation forms, and that because they're Dirichlet integers, you can call the icosions, if you want, you could call them an icosionic, you can call them a Dirichlet integer subset of the quaternions, right? Meaning instead of calling them icosions, another nice name would be a Dirichlet integer subset of the quaternions. So it seems that there should be a Dirichlet integer subset of the octonions.
Yeah, this is what I was talking with Ray.
Yeah. And if you exclude sign values, right, the quaternions, they don't have 7 plus 1 sign, they don't have 7 plus 1 values if you exclude, excluding sign values. But the octonions do, and so it compresses to 7 plus 1 values, if you ignore sign values. So what we have been thinking about is whether or not there's an opportunity to discover an analog in the octonions of the icosions, where one could call it the quaternion Dirichlet integers, and then these octonion Dirichlet, so
because anyway, look at his book, because Ray was thinking that maybe the Sedenians could do it. Anyway, essentially you have it's what they call lattice Hopf vibration. SU15 vibrates to S7 and there's an S8 in the fiber. So what Dyson wanted to play is work with the 16-dimensional lattice, and then you compactify 8 dimensions on an E8 lattice, and you get some sort of Elser-Sloan version, but in 8 dimensions. So this is for you to, I think it's an interesting project for you guys to do. Construct a quasicrystal in 8 dimension, which is the 8-dimension analog of the Elser-Sloan. So I think that would be an interesting project.
Well, by the way, I left one piece out. I think I lost.
Now with the octonions and the golden mean, of course.
So I lost you because I didn't explain why these root vectors from E8 compress. It's because when you go to 3D and you measure the lengths in the 3D projection of E8 to 3D, you have 7 plus 1 values, 7 Dirichlet integers, 1, 0, but all of those values were exactly a unit root vector of E8, so they get compressed in the 3D. And
they have to be deformed. Once you project, then you deform them.
There's 8 of them, 8 deformations.
Yes.
But there's a small problem there when you compare it with octonions, because the integer octonions are not like 7 plus 1.
I know.
So you have actually more when you do the integer approximation for octonions than 7 plus 1.
That's
so it's not one mapping.
Yeah, I mean there are 8 integral octonions, right, that have a 7 plus 1 form, because one of the 8 is 0 and the other 7 are not.
the rest, the 7 are imaginary, but you can do integer. When you say integer octonions, you don't just mean taking the integer part of each octonion that's left.
Right. That's,
so you have an approximation with more integer numbers than just the 7 plus 1.
You're right. That's the fly in the ointment that is that's not clear. So I thought maybe you could chew on that problem.
Yeah. Well, I'll think about it. Yeah, but anyway, Ray has worked with Sedenions, so I wouldn't be surprised that Sedenions may play a role here, because S15. Remember, S7, the 7th sphere encloses an 8-dimensional bulk volume, the E8, for example, and then the S15 sphere encloses a 16-dimensional bulk. Yes. So Sedenions, I wouldn't be surprised that Sedenions will.
So Sedenions relate to 7 spheres.
No, Sedenions will to 15 spheres, because they enclose a 6-dimensional bulk volume.
But then I think it's going higher demand, more complicated. I think your think is more. It's more like it's easier with quaternions because quaternions.
Well, look, quaternions are associative,
and they are the group SU2. So you look finite groups of SU2.
Yes.
So
with octonions, it's more subtle because they are.
And then you map to the icosian.
Yeah.
But octonions.
They are non-associative. Yeah, you have to look at. This is why you have to look at the left action or the right action, because the non-associativity is going to screw things up. So you have to look at the left action or right action, because when you multiply 3 things together, you have to be very careful in which order you perform the operation. So things are more subtle. It's not that trivial, but anyway, but geometrically, the picture is there somehow, you know. So I think it will be an interesting project for you guys to do, because, and the reason the 16 lattice is very important is because in string theory, E8, 2 copies of E8 or SO32 is the anomaly free group in string theory. Which is it came from string theory.
Heteronic string theory.
When you look at the anomaly cancellation, it only occurs for those groups, you know. So and the 16 lattice, and then of course you can work with the Leech lattice in 24, and then you can go to the monster group, because I've been having a lot of conversations with Mike and David about the monster group. But anyway, we could think about that later. But let me just continue.
Since you brought Mike and David here, you were mentioning the 2 copies of E8 from Molina, and then Mike has his idea of 3 copies of E8 to have his degrees of freedom, and then Garrett Lisi is like 1 copy of E8. And what I'm interested in is exactly the number of degrees of freedom that you're having for the fermions, because they, depending on the production mechanism, they can constrain the mass of your particle. And for example, one of the idea that Mike, because Mike is looking at like 3 copies in order to explain, of course, the dark matter part. And I know that the number of degrees of freedom one needs is in the thousands. So I'd be interested to see exactly between these models, like how many degrees of freedom you get per combinations. Because I know with 1E8, I mean, I spoke with Garrett about this, and I don't think with 1E8 you have enough degrees of freedom to have such a higher, such a massive fermion. 2 copies may be enough. I know Mike is looking at 3, so I was curious from your model, like exactly how many degrees of freedom you would have at the
Well, Mike, Alessio, and Piero, and David, because they have been working with this exceptional periodicity, and they wanted to extend everything in multiples of 8, you know. Because many years ago, Wilson, a mathematician, gave an octonionic implementation of the Leech lattice. And the Leech lattice is 3 copies of 8. 3 times 8 is 24. And the Leech lattice is very important because when you have a bosonic string in 26 dimension, you compactify 24 dimensions. So you go from 26 to 2 dimensions. Because 2 dimensions is the world sheet of the string. So the Leech lattice lives in 24 dimensions. And this is where you get the monster group. Because the automorphism group of the string Berkeley's operator algebra is the monster group.
And we know it's also proven to be the maximal packing of n spheres in 24
dimensions. Yes, the Leech lattice. So, but because Robert Wilson worked with octonions, 3 times 8 is like having 3 copies of the octonions, and gives you 24. So this is why Mike is very excited about working with.
No. So exactly. Sorry, just 1 second, because I want to clarify this. So exactly what I meant is like the number of degrees of freedom is going to be translated in the mass of your particle. And Mike is having now with his models with Alessio and Piero 2048, which would be transferred to something like keV range. So I'm not sure about the 2 copies of E8, if they have still something in the orders of 1,000 degrees of freedom for fermion production, but I was curious in your model if you can predict like exactly how.
Well, but here I have to look at, well, then you have to look at the
because I know one E8 can't do it.
No, you have to look here. Look at SU4 representations. Really, I'm just looking at Look at representations of SU4.
Yeah, but it depends on how you kind of combine them to give.
Because
the freedom. You have one massive electron as well. So
let me just the way I combine. Okay, let me see. Let me just go back to the way I embedded the ordinary fermions or in quarks into my SU4 multiplets. I just look at the fundamental representation. Let me just go back to the to the way I. Let me look here. Let's look at here. This is my first family. So look at the way I embedded the up quark and the down quark. So this is how. So here essentially, I embedded. So this is how I do it. So you're looking at the number of degrees of freedom that this matrix has, for example.
It depends on how you combine it, like in the neutron and electron case, because depending on how you combine one, you can have a certain number for the other or the other way around.
Yeah, well, I need to write down the Dirac-Lagrangian for my fermions, and then I can tell you more or less how you combine, So I haven't written the matter Lagrangian, because then I have to introduce the Higgs sector. But what I do have for my gauge fields, remember I have a lot of extra gauge bosons, and this reminds me of the leptoquarks. Remember when you have the SU5 unification, you have these leptoquark gauge bosons. Because remember, I also have a lot of gauge bosons, So I do have, okay, in terms of degrees of freedom, okay, the standard model has SU3, SU2, SU1. So you have 8 gluons. You have 12 gauge fields, but here I have 64 gauge fields, 64. So I have a lot of extra gauge fields. So when I write down my Dirac-Lagrangian, I'm going to have a lot of freedom, a lot of freedom to combine my Dirac-Lagrangian with my quarks and my gauge fields, because I have 64 of them. Yeah, so I have a lot of freedom here. Yeah. But probably less than 3 copies of E8. Yeah. Because remember, E8 has 248 gauge fields. Here I only have 64. So it's much smaller.
How many gauge fields would you guess that A8 has? Because E8 is 3 copies of A8. Should it be the same?
Well, let me see. E8 has 248. Now A8, you mean SU9 or what?
SU9 has 80 years.
SU9, you take 9 times 9 is 81, and you subtract 1 has 80.
So you get 3 copies and get to 240.
Yeah, but remember 240 is the number of roots, but you have to include the Cartanza.
The basis, so you get 248.
Yeah. Let me just go give you a little bit more about the history of the reference, because it's important to, in case some of you.
My question is, when you have the metric, what are you doing with the metric? Einstein equation?
Yeah. Essentially, what I have here is a metric with extra indices. So what I'm doing in a very pedestrian way is I'm coloring the graviton. So what I do, I'm having extra indices to the metric. So in other words, another way of represent that metric, instead of having a 4x4 matrix, I have really a 16 times 16 matrix.
At the beginning, Klee asked about, you are talking about mathematics, but then there are word gravity. So at this level, the physics and the mathematics is very mixing, right? You have an algebraic structure. You say that this is a gauge field, or
but remember, but here everything is gravity. Gravity really contains everything. In other words, what I'm doing is a Kaluza-Klein in disguise. So I'm threading my extra dimensions for my algebras.
So everything's made of gravity.
Yes.
You know who said that?
Yes, exactly.
Cassiopeians. Everything is made of gravity. And then Richard said everything's made of curvature. Every time there's a twist, yeah. This is really good, Carlos. Thank you.
Yeah, let me just continue with the reference before you guys leave. Okay, I wrote a paper on on the mathematics. Anyway, now this, don't forget, I keep reminding Ray, don't forget this monster paper. It's almost 2,000 pages. Here he gives you all the way you can construct unified model buildings in 4 or 5 dimensions and rank 16. Don't forget this paper. This paper is absolute. Yamatsu. Yeah, this paper is almost 2,000 pages long. Don't forget. This has everything you need.
Archive accepted. I'll read it tonight.
No, because he has. If you want to look at unified model building, he gives you all the possible combinations of unified model building. Anyway, so do I have more? Anyway, here these guys work with SU3 family extended trinification. Yeah. And this guy is the only person that I know of that has worked with non-symmetrical Kaluza-Klein theorem. Anyway, these are the references. Anyway, so I hope you enjoyed it. I hope.
Really good.
Yeah.